comes out of section 8.6, logarithmic differentiation. I actually want to do something a little unusual for our purposes here. We know from way back that if y equals x to the n, right, and the some number, that the derivative, we just use the power rule, we said n times x to the n minus 1. I want to use this log differentiation to show that that's true. Because if you look way back in chapter 2, we really only showed that it worked for a nice whole number exponents because it involved factoring. The proof of the power rule there involved factoring. So we know that, for example, y equals x to the fourth, the derivative is 4x cubed. And that was proved through a bunch of fancy polynomial factoring. We've been using the fact that, if this is y equals x to the 1/3, we still use the same rule to say, 1/3 x to the negative 2/3. But we never really did prove that. If we prove it right here, it's actually relatively simple. If we say ln of y equals ln of x to the n, use our log rules to say, well, bring that power down front. And if I take the derivative, I've got y prime over y equals n times 1 over x. So y prime equals n over x times y. Now that doesn't seem like the power rule, but if you go back to the beginning and say, well, y was just x to the n, what you have here is n times x to the n over x, which is n times x to the n minus 1. So you can show, without too much nastiness, that the power rule works. I want to make a big distinction here between derivatives where you've got the base as a variable and the exponent as a number. And we've been able to do those derivatives just like we just did above with the power rule. We've also now in this chapter run into the base as a number and the variable as an exponent. Now I want to make sure you distinguish between those because that's a very different situation. What we found when we took the derivative of this was we ended up with 6 to the x times ln of 6. So just be straight on which rule you're using and which kind of derivative you're taking. What we'll be able to do is, as we go on with these, if you run into a situation, unusual situation, where you've got a variable in both places, you can actually use log differentiation to do that. So say, for example, I had y equals x to the x. It doesn't fit into this category where the base is a variable and the exponent is a number. And it doesn't fit into this second category where the base is a number and the variable is an exponent. It's a bit of both. It's got a base that's a variable and an exponent that's variable. The only way really to go about this is not to use either of those rules, but to use logarithmic differentiation. Say, okay, let's log both sides. The reason why that's useful, oops, the absolute value sign can be outside there, but ln of y equals x times ln of x. Now I take the derivative of everything with respect to x. I get y prime over y equals, now be careful here, you do need to use product rule. I've got x times 1 over x plus ln of x times 1. So if I take that a step further, I say y prime equals y times all of that. Now x times 1 over x is just 1, and I've got plus the natural log of the absolute value of x. So the derivative of this is x to the x times 1 plus the natural log of the absolute value of x. Strange derivative. I couldn't use regular power rule. I couldn't use regular exponential function stuff. What I use is logarithmic differentiation to come up with an expression for derivative that I could put in a value of x and find a slope.